Okay, so good morning, everyone, and thanks to the organizer for inviting me to give this talk today. So today I will talk about stable stratification in planetary interiors, and in particular, what kind of constraints we can get from the magnetic field and from numerical dynamo models to put on possible stable stratification in planetary interiors in terms of location and possibly amplitude. And so the talk I will give today is organized as follows. I will first show you surface magnetic maps of the radial field of planets, and then I will show you where there are possible stable stratification in planetary interiors and what could be their influence on the magnetic field generation. I will then briefly introduce the MHD model we use to try to model this stable stratification, and present you two series of models, first being the geodynamo model with a stably stratified layer underneath the core mantle boundary, and then in the second step, gas giant models where we introduce an intermediate stably stratified layer. And so to begin with, the figure you see here shows the maps of the radial component of the magnetic field for the 6 planets of our solar system, which have a magnetic field of internal origin. And so those maps have been constructed by combining observatory and satellite data in the case of the Earth core. And then for the other planets, use either flybys or orbiters when they are available. And so from this map, you can draw several lines of separation. And the first and most obvious one being based on the degree of dipolarity of the field. And you can draw an immediate separation between the fields which are dominated by the axial dipole, so Mercury, Saturn, the Earth, and Jupiter, and the fields which are clearly not axial, that we call multipolar for the ice planets here. A second way of separation is based on the amplitude of the surface field. And here you can separate between what we could call a strong magnetic field at the surface with respect to the available buoyancy power you expect to fuel this magnetic field. And it will be the case for the Earth or for Jupiter in comparison with, for instance, Mercury or Saturn, which feature a much weaker field. And this weak field could be the signature of internal processes that damp efficiently the magnetic field amplitude when it comes to the surface. Finally, the last way of sorting has to do with the complexity of the field you observe at the surface. And this complexity or this lack of features could come either from the lack of resolution, because you don't have enough flybys and data, and so you're able only to reconstruct a large-scale model of the field. Or it could come from internal processes that smooth out the complex feature of the field, and this is particularly the case of Saturn, where the Gastine orbiter provided enough data to build a sufficiently accurate model up to at least a spherical harmonic degree of 10. And despite this spatial resolution, the magnetic field we obtain is fairly simple, almost perfectly axisymmetric. And again, this might point toward physical effects that are responsible of smoothing out the field inside and removing most of the non-axisymmetric features. So if we now focus on the two planets I will mainly talk about today, and downward continue the field up to the top of the dynamo region, which will be the Earth's core mantle boundary, and something like 10% below the surface of Jupiter, we are magnifying the small-scale feature of the field, and so we still recover dipole-dominated configuration. But for the Earth core, we now reveal these flux concentration structures and regions where the polarity of these patches are the opposite of the dominant polarity of the dipole. If we now look at Jupiter, we observe a fairly different structure with some elongated structure which are fairly aligned in the east-west direction, like here in the equatorial region. Also strong flux concentration here in the north, or here in the equatorial region with what's called sometimes the great blue spot, though it probably is a choice made by people who choose a different color maps than displayed here. And so overall, also there is a symmetry, a stronger field in the northern hemisphere than in the south. So now if we look at the internal structure of planets with a peculiar focus on the region where the magnetic field will be generated, you have to look in region where you have an electrically conducting fluid, which will drive your magnetic field via dynamo action. And this corresponds to the liquid outer core of terrestrial planets, Mercury and the Earth here, which is mainly made of liquid iron plus some lighter elements. Now, if you look at the gas giant planets, there is an envelope made of hydrogen and helium. And when you go deeper and deeper with the pressure increase, there is a phase transition of hydrogen towards the metallic phase. And this happened roughly 10% below the surface. And so here in this part, hydrogen become metallic. And so if you have convection or motion there, you can sustain the magnetic field via dynamo action. So if you go even deeper here, the recent gravity data suggests that instead of having a compact core, what could happen is possibly a linear or a continuous growth of the metallicity towards the center. And so you would be in favor of maybe having a diluted core that could possibly behave as a stably stratified region, of which the size is not completely known at this stage. For the ice planets, little is known because of the lack of gravity data, but again, the standard model, I would say, assume a layered system where you would have a molecular envelope and then a phase transition of water towards the ionic and superionic phase that could be able to sustain the magnetic field of these planets. So now if I sketch the region of interest today, so I put here the convective regions. You also notice that I put some regions here with question marks that could be possibly stably stratified. And those are regions just underneath the core mantle boundary of terrestrial planets. And so these question marks come from several independent studies coming from seismic studies, mineral physics, and I will come back to that in a minute. If you look at the gas giant planets, there are also regions which are convecting in the external parts and here, but there are also possible regions where stable stratification could occur. This could be the case here so there is some ab initio simulation suggests that helium could demix from hydrogen in a range of pressure that would correspond to this layer here. And so in that case, you would form droplets of helium that would penetrate deep and then remix with the metallic hydrogen deeper down. And so it would create a situation where you have a stabilizing gradient of composition and a destabilizing temperature gradient. So you could be in that case either in a double diffusive regime of semi-convection or maybe in something which is stably stratified. And the same could more or less occur here in the center. So if we go back a bit more in bit more details for the Earth core, so there are several seismic studies that use SMKS wave to probe just the region underneath the core mantle boundary. And so those waves reflect m-1 times just at the core mantle boundary, and so they are particularly useful if you want to look at the region here. And what they found is that they found a p-wave velocity which were actually smaller than the preliminary reference Earth model. And this difference has been attributed to a possible stratification of chemical composition, which could range from 100 to 400 kilometers underneath the core mantle boundary, and with a strong degree of stratification in terms of Brun-Weisser frequency normalized by the rotation rate with order 10 value. And so I must stress that there is no consensus on that. And for instance, Irving and collaborators in 2018 attributed the difference to Prem rather to subtle changes in the equation of state. There are independent and additional constraints that come from mineral physics, and in particular, ab initio calculation and high pressure experiments suggest that the core conductivity, the core thermal conductivity, could be in a kind of a high range value. And in that case, the entirely convecting scenario would be quite tight in terms of global energy budget. And so in that case, you would end up with a thermal stratification, very likely atop the core. But again, on this one, there is no consensus, and other groups rather favor the low conductivity scenario. And in that case, the entire convective scenario would be more likely. So now if you have a stably stratified layer underneath the core mantle boundary, you are prone to excite a new variety of waves. So on Tuesday, we've heard a lot about MC waves, so where the magnetic and Coriolis force as the restoring force. But now if you have a stable layer, you are also adding the Archimedean force as a third possible restoring force. And so you excite a new category of waves that are called Mach waves. And so already in 1993, Braginski invoked those waves as a possible candidate to explain the decadal time variation of the geomagnetic field. So more recently, Bruce Buffett showed that if you can find an optimal to explain the variation of the axial dipole at the surface over the last 80 years, if you consider a stably stratified layer of a thickness of 140 kilometers with a moderate degree of stratification with typically n order of omega. Now, if we look at the giant planets, so there are a lot of gravity measurements that have been gathered by the recent space mission Cassini and Juno. So it provides more and more constraint on the mass distribution inside those planets. But there are also constraints coming from seismology, especially in the case of Saturn. So you can measure, or you can identify gravity mode signature in the rings oscillations. And so it puts you some constraint on the G-mode cavity inside Saturn. And so what has been done by Mankiewicz and Fuller very recently in 2020 is to conduct an array of internal structure model and kind of find the best fit scenario that both fit the gravity and the seismic constraint. And that's what's displayed here on the left. You have metallicity as a function of the normalized radius inside Saturn, density, and then maybe more interesting for us today, the normalized Brun-Weisseler frequency. And so you see here in this yellow area the favor model that show a positive Brun-Weisseler frequency over the innermost 60% of Saturn. So it could mean that most of Saturn's interior could be stably stratified. So what could be the physical effect of such a layer? So we are talking about planetary interiors which are heavily rotationally constrained, low Rossby number. So the question you want to ask is how rotating convection penetrates into a neighboring stable layer. And so this question has been addressed by Takehiro and Lister in 2001. So they considered a linear model, and they showed that the distance of penetration of convective structure is directly controlled by the ratio of the Brun-Weisseler frequency over the rotation period, and also depends on the horizontal size L of the convective columns that impinge into the stably stratified layer. And so as an illustration, you see here three configurations. So bottom part is convecting, upper part is stably stratified. And here you just decrease n over omega, and you see that your convective structure are either penetrating the whole way through or are rather confined in the underneath convective region. Now, if we look at the magnetic field, and you ask yourself what could be the effect of such a layer on the magnetic field, you can place yourself in a limit where the stable stratification would dump almost all the flows that are developing in this layer. And so you would be in a position where you have a conducting fluid layer with no motion. And so if you have a time variable field just underneath, this time variability of the field will be damped by skin effect over a typical skin depth, which directly relates to the magnetic diffusivity of the fluid times the typical time scale variation of the magnetic field. And since the small scale features will vary with a faster time scale, you anticipate that your smaller scale feature of the field will be damped much more efficiently than the large scale. And so as an illustration, I took an example from Uli's calculation for Mercury from 2006. So you see that here, this is a convective region, and beyond the dashed line, it's stably stratified. Now you look here at the radial component of the magnetic field at the top of the convective part. It features a lot of small-scale pattern. It's actually not that dipolar at all. And when you look at the surface field, it's really smoothed out a lot, and a large fraction of the smoothing can be attributed to the skin effect, which takes place in this huge stably stratified layer. Okay, so to try to work on this topic, we will consider numerical models, so dynamo models in 3D rotating spherical shell. And we will be able to incorporate stable layers that are either located close by to the core mantle boundary or somewhere in the middle to mimic the influence of helium demixing. So we'll be considering either anelastic or boostiness models, and I will use the pseudospectral approach. That means that your horizontal direction are expanded in spherical harmonics, and the radial direction is expanded either in Chebyshev for finite differences. And in that sense, it's still very close to the algorithm put forward by Glatzmeyer in 1984. So I will be using the magic code in combination with the SHTNS library for the spherical harmonic transforms. So to begin with, I will show you a configuration for the geodynamo where I incorporate a stably stratified layer just beneath the core mantle boundary. This corresponds to the dashed region here. I will be able to vary the thickness of this layer and the degree of stratification by playing with the ratio of Brun-Weisser over omega. So the rest will be convecting, and I will also have a rotating and conducting inner core. Okay, so the snapshot you're seeing here shows the radial component of the velocity for 3 numerical simulations with decreasing Ekman number and a moderate degree of stratification close to 1 and close to the optimal value put forward by Bruce Buffett in 2016. So the stably stratified layer is roughly 200 kilometers thick, and it's demarcated here or delineated by this black line. So the main difference between the 3 setups is the Ekman number and Rayleigh number combination. And so you start from a fairly large scale flow, and you see that when I decrease the Ekman number here, I start to develop smaller scale, especially in the vicinity of the edge of the convective regions. Now, if you look at the meridional planes here, you do see that the convective structure penetrates very efficiently in the upper stable regions. You have a lot of flow here. And this is not so much the case any longer when you look at this one, at lower Ekman number. And so it means that the penetration distance has a strong dependence on the convective flow length scale. So if you want to be a little bit more quantitative on that, you want to find a good measure of the penetration distance. And so what I show here is the radial distribution of poloidal energy, kinetic energy, and buoyancy power for 6 numerical simulations, an entirely convecting one in blue, and then cases where I have a stably stratified layer, which is shown demarcated by this black line, and an increasing degree of stratification. So you see that the poloidal flow is quenched more and more when you increase the degree of stratification. And maybe more interesting here is the buoyancy power profile. So in the convective region, it's positive. You're driving your convection by positive buoyancy power. And when you turn into the stably stratified layer, there is a little dip, a little sign change of this quantity. And this comes from the fact that if you have an upwelling that enters into a subadiabatic region, then the correlation of the radial velocity with the temperature fluctuation will get negative. And so this kind of profile has been used, for instance, by Matt Browning in 2004 to provide an accurate measurement of the distance of penetration in stellar models. And so basically, I did the same here. I reused the definition introduced by Matt and showed that it provides an estimate of the distance of penetration that is shown here by these segments. So if I do that in a systematic manner and show the distance of penetration as a function, especially on the right panel here, as a local Brun-Weisser frequency over the rotation rate, times a measure of the horizontal scale of the flow, I can see that my different configurations, so the different colors here corresponds to different thickness of the stable layers, and the different symbols correspond to different Ekman and Rayleigh number configuration. I basically find 2 branches of solution. So the horizontal one corresponds to the case where the convective eddies are able to penetrate and cross the entire stably stratified layer. And the dashed line, where you see a very good agreement here with the Takehiro and Lister, so which means that the linear the linear theory put forward by Takehiro and Lister on convective penetration is well satisfied in this nonlinear calculation. And so it means also that the magnetic field here has little influence on the distance of penetration of the convective eddies. So now if we look at the magnetic field, so on the left is the core mantle boundary spectra of the magnetic energy as a function of the spherical harmonic degree for the 6 same simulations. And on the right, the magnetic energy spectra of a stratified case normalized by the fully convective counterpart. And so it's kind of a measure of the damping. And so you see that the damping is scale dependent, and it's much stronger at small scale than at large scale. Now, if you want to check whether skin effect provides an accurate description of this, you have to keep in mind that, again, skin effect will work only if you have no flow. And so in this limit, you could assume that the CMB field will relate to the field at the upper edge, at the lower edge of the stably stratified region, with an exponential law that involves the thickness of the stably stratified layer and the skin depth. And this is expected to work only when you have almost no flow. And so if you look how it compares, this is the dashed line here. You see that you indeed come to an agreement with this dashed line only if your degree of stratification is large enough, so beyond 15 or so. Practically, it means that you expect that the magnetic field will be smoothed a lot by this stable layer. And to show that, I selected 4 cases with increasing degree of stratification. So each time it's a 200 kilometer thick stable layer. You have the radial component at the CMB and just at the top of the convective region. Here in the entirely convective feature, they feature a lot of reverse polarity patches, small scale feature. But as soon as you put stable stratification, you decrease the amplitude a lot. You see it by the color getting fainter and fainter. But you also smooth out the small scale and get something much large scale, removing most of the reverse polarity patches. So it already tells you that it's going to be very tight to produce an Earth-like dynamo model as soon as you start to increase the too large degree of stratification. If you want to quantify that, you can use the rating parameters introduced by Christensen and collaborators in 2010 that try to estimate the Earth-likeness of a field produced by the dynamo model in terms of 4 parameters. One being the degree of the axial dipole component. The second one, the degree of the symmetry of the field at the core mantle boundary. The third one, the zonality of the field. And the fourth one being, or quantifying, the ability of the field to produce localized patches. So from these 4 rating quantities, you can build a chi-square, which is a global measure of the agreement of your simulation or your dynamo model with a modern geomagnetic field. And so this is what's color-coded here. And you see the 4 individual rating parameters as a function of a quantity named HF, an effective thickness, which is simply the difference between the static thickness of the stably stratified layer minus the penetration distance. And so all the best Earth-like models are blue here. And you see that for all individual rating parameters, the best fit is obtained very close to 0. So in other words, it means that HF has to be 0 to find the best Earth-like model. So the penetration distance has to be equal to more or less the thickness of the stable layer. So since we established a scaling for the penetration distance, and we've just shown that this penetration distance has to be equal to the thickness of the stably stratified layer, you can end up with this theoretical bound, which relates n over omega to the thickness. And indeed, if you now compute a systematic survey for a fixed Ekman number and vary those 2 parameters, the best Earth-like cases, which are these big blue circles, all lie below the line. And all the cases above are too smooth, too simple to be Earth-like. And in particular, now if you go back to the seismic studies that gave a very large estimate for n over omega, it seems to be very unlikely to produce Earth-like magnetic field with such a large degree of stratification. So now there are 2 dots underneath the line that could still work, the Bragg 93, the Buffett studies from 2016. But here you have to keep in mind that this array of simulation has been conducted with one fixed Ekman number. And so the length scale, the horizontal length scale that still is here, is more or less fixed. And so if you want to check the validity of this scaling, you want to change the Ekman number too. And so that's what we've done. We just selected 3 setups, entirely convecting, and then 2 degrees of stratification, and then change the Ekman number. And what we see is that the entirely convecting remain in the category of excellent agreement with the Earth core. But as soon as you decrease the Ekman number, or you move towards more and more kind of Earth-like regime, then your cases with stable stratification start to deviate more and more. And so this second plot tells you that from the dynamo modeling perspective, it sounds quite unlikely that you could maintain stable stratification in the modern, to explain the modern field. So now let's turn to the second configuration. So I will be presenting some results on gas giant planets. And again, the purpose here is to try to check the influence of a demixing layer, which would happen when helium starts to rain down. And so we will consider setups where it's convecting here, stably stratified, and then convective again. And so we won't play too much the game of a diluted core, or we will just consider that there is something we don't model here in the center, and so we won't include any additional stable layer inward. So to do that, to model this layer, I simply consider kind of an ad hoc entropy gradient profile that is getting super adiabatic in some places, and this is subadiabatic in the rest. And so by doing that, I can easily tune the location and the degree of stratification of this layer. And then the density and the electrical conductivity of the numerical model in orange are fairly close to the internal models of Jupiter from French et al. So I will be mainly presenting one simulation where n over omega is very large, of the order 10 here in the stable stratified layer. So the first plot I'm showing here is the radial velocity in the equatorial plane, and the 2 dashed lines mark the location of the stable layer. So you produce large-scale convection in the dynamo region, small-scale flow in the non-conducting layer, and in between you see a nice quenching of the flow because of the stable stratification. So if you look at the kinetic and magnetic energy distribution as a function of radius, and again the power source and things as a function of radius, you see that in blue, the magnetic energy is more than 1 order of magnitude larger than the kinetic one in the metallic core. And then when the electrical conductivity decreases outward, you have a rise of the kinetic energy. And in details, this kinetic energy is dominated by this dashed line, which is the toroidal axisymmetric energy. So in other words, you're producing jets, differential rotation in the external region here. And you have a nice separation between magnetic and kinetic energy at depth. And so it's a good hint that at least the basic ordering of forces are correct in this model compared to our current understanding of gas giant planets. But now if we look at the surface field such a model produces, so this is a snapshot of the radial component of the magnetic field, you see that we lost this east-west structure that I was talking about in the intro. We don't have enough flux concentration, and it comes out very clearly if you plot the surface spectra of the magnetic field. So in blue is the Connerny model based from the first Juno data, GRM09, and in orange is the numerical simulation, and you immediately see that you lack a lot of energy in the small scale compared to what you should get. Now, another important aspect here for the gas giant planets is the surface jets. So the fact that you will produce alternated jets as observed on Jupiter. So on the left is an entirely convective model. What's displayed is the zonal velocity. So red is prograde, blue retrograde. And you see that you produce a strong prograde jets here, but nothing like alternated jets at high latitude. And as soon as you incorporate this stable layer, which is shown by this dashed line, and as soon as the degree of stratification is sufficient, then you start to produce faint but alternated jets, successively retrograde and prograde, like here at mid-latitude. And so this is encouraging that maybe this layer is able to help to confine the jets in the external regions. So it's time to conclude on this. So the question I raised initially is stable stratified layers in planetary interiors. And there is a question mark here because there are a lot of uncertainties regarding mineral physics, seismology, and interpretation of the data. And so there is no clear answer whether there are such layers or not. So the point here was to put some constraint using dynamo models on such layers. And again, the two main physical effects you can anticipate by incorporating these layers, not talking about waves, are the penetrative convection phenomena, which we showed agrees very well in the numerical 3D calculation with the linear theory by Takiro and Lister, and the smoothing of the magnetic field via skin effect. So in more detail, for the geodynamo, we showed that the strong stratification scenario put forward by some seismic study sounds to be very unlikely in the light of geodynamo models. The most moderate n over omega equal 1 might be maybe conceivable, at least high Ekman simulation suggest it, but lower Ekman simulation don't. And so which means that it sounds also quite unlikely that when you move towards more and more Earth-like parameters, even those parameters, this moderate degree of stratification could be maintained. So maybe there is an option for regionalized stratification, but this remains to be checked in a systematic dynamo models. About the gas giant planets, I just show you that if you incorporate this demixing layer in the mediate, so in this intermediate stably stratified layer, you don't get the magnetic field structure right, but you start to produce multiple jets. So maybe some way out here would be to shift upwards the stably stratified layer, as done, for instance, by Kimi Moore and collaborators in a recent paper. Or maybe we also have to keep in mind here that in contrast to the geodynamo models, we are facing a lot of troubles with the magnetic Reynolds number. And this is in a way a bit similar to what has been discussed for the stellar models. That is, here we are bound to use RM 1000, while the expected value for Jupiter is more in the 10 to 4, 10 to 5 regime. Okay, so as an opening, I just want to stress that here, most of this stably stratified layer might actually be double diffusive. And the reason why is that the density anomalies in planetary interiors are driven both by thermal and compositional anomalies. And so in that case, it could well be that you could face fingering or semi-convection and not stable stratification. So both of these regimes, fingering and semi-convection, they are prone to harbor very large-scale instabilities, at least according to the planar local models. But there are a lot to be done because little is known on the influence of spherical geometry on these instabilities, not even talking about rotation and magnetic field. Really, there is a lot to be done here. And so as an illustrative example, I show you here the absolute vorticity of a rotating fingering convection in a full sphere done by Monville and collaborators. And here on the right, semi-convection simulation. So this is non-rotating, but you see that here the chemical composition is spontaneously creating layers which are prone to merge and evolve over time. And with that, I thank you for your attention.
So, thank you very much. Time for questions.
Thanks, Thomas. That was a great talk. I have, I guess, a question, about the role of the light scales in terms of deciding whether or not the convection penetrates. You know, when we think about the buoyancy sources for the core, we often think of them being primarily generated from the inner core. So chemical buoyancy, latent heat due to inner core growth. And we generally think of the amount of heat flux or buoyancy generated at the top as being quite small, right? And so, for example, in Julien's models, he actually sets the buoyancy to 0 at the top.
Yeah.
And so the point, I guess, is that when you're running your calculations, it looks to me like you have actually a substantial heat flux through the top. It looks like you're generating that very small-scale convection at the top. And so the point, I guess, is that when you have that structure, which we don't expect in the current field, and you change the Ekman number to lower and lower values, you make that length scale that you talked about smaller and smaller, and then argue that you can't explain the stratification. I think that's largely because of the nature of the models that you're running.
I wouldn't be so certain, and the reason of it being that what happens is that, let me go back to that. So what happens is that here you have a sign change of the buoyancy power, and so it means that locally you will just be passing the onset of convection. And so if you're in a rotating system, you're really prone to develop the onset scale just at the edge of the layer, just because locally you're passing just the onset criterion. And so I don't see why it should be different than that, actually.
Well, but it's different because your comment is that it depends on the horizontal length scale, right?
Yeah.
And so the point is, I will be willing to bet you that in Julian's calculations, you don't see that small scale convection at the top of the core, simply because there's very little buoyancy at the top of the core.
Maybe I can comment on that.
So you're right, Bruce. Indeed, in the calculations that I do with no buoyancy, neutral buoyancy at the outer boundary, you don't have those structures. But I think everything can be still rationalized because the criterion written by Thomas is basically that you will get penetration if the time scale of the motion that occurs right under the boundary is favorable with respect to the time scale corresponding to the Brun-Weisela frequency. So the criterion that Thomas has written with the scale can also be translated in other configurations where you have other types of time scales beneath the outer boundary. And in which case, I believe what happens is that the conclusions that he has presented here are largely unchanged. That is, the magnitude of the skin effect and what he predicts is largely unchanged with respect to the change of boundary conditions.
Okay.
Thanks, that was a really nice talk. My question is concerning the main takeaway with the stable layer seems to change the differential rotation and you get multiple jets. Do you have an idea of what's causing that in terms of, is it altering the structure of the Taylor columns? Like, something must be transporting angular momentum, I guess.
Yeah.
Or is there a circulation or something like that?
Yeah, exactly. So what happened is that you have a slight penetration of the meridional circulation into the stable layer, and it just modified slightly the entropy distribution. And so you have a ds d theta, kind of a gradient, a lateral gradient of entropy. And so it helps to quench and create this z gradient of zonal flow. So it's a thermal wind effect. And so indeed, yeah, the fact that you're having this stable layer is changing the force balance locally. And so that's why you can do that. So the problem being that here in this setup, so if you would produce jets, they would cross all the way or being quenched by the magnetic field. So if you start to produce a jet, it's rapidly rotating, so it has to be on cylinders. And so if you have a strong field at depth, it will quench it here, and then there is no way you can produce jets.
Okay.
So it provides a kind of a jet quenching alternative mechanism by just enforcing the flow to be zero here.
Okay. Okay, thanks.
Thank you, Thomas, for this nice talk. Just I have a short question. I have a feeling in the strong stably stratified regime that you can get the same result if you consider separately each zone, for instance, the convective one or the stably stratified zone. Did you notice some new physical processes in which you have interaction between the different layers in this regime when the Brun-Weisela frequency is much larger than the rotational frequency? And I'm also surprised on this slide because in your established stratified layer, you don't have a spherical symmetry that is expected when the buoyancy frequency is much higher than the rotational frequency.
Yes, so you're right. I mean, there are differences, and again, the skin effect is kind of the end member you would get when in the limit of very strong stratification, and you see already that here, for like moderate values, you do not follow the theoretical scaling, so which means that there are some flows penetrating in there. So, but to answer more precisely your question, I didn't really look into details of additional phenomena like waves. For sure, there are gravity waves excited in there. But well, my main focus here was just to see the static influence on the field. And so, yeah, I didn't look for specific additional effects here.
Okay.
Yes, I'm a bit thinking out loud here, but couldn't we, for the stratification in the Earth core, couldn't we reverse a little bit the argument and say, since we see convective structure through core flow inversion that have a given size, like a few 100 kilometers, can it just give a constraint on the stratification layer like that?
Well, I would tend to say that, yeah, if you see them, it means that either they have been damped quite a bit, and so they would be much larger underneath the core mantle, the stable layer, so that would give you, I don't know, well, you would need to characterize the uprise of the value of the convective flow and see what kind of value you would end up in the convective region, but that would be too large, I think, regarding the secular variation of the field. I don't know, maybe I'm wrong, but.
I would have a question. You mentioned that one possible solution to retain small-scale structures in the surface magnetic field of Jupiter if you had a higher magnetic Reynolds number. However, a higher magnetic Reynolds number also means that your fluctuation time scales become shorter, so the skin effect in a stably stratified layer would be more pronounced and even filled out these structures more effectively.
Yes, but it will also change the degree of dipolarity a lot at the top of the convective part. And so that's where there might be a room, because your field will be on average less dipolar if you increase Rm here as compared to what it is now, quite substantially at least, I think. And so, of course, you will be damping it more, but since you're gaining here, I don't know. It remains to be checked, I think.
Any further questions? Yes.
So with a stable layer, you got these alternating jets at higher latitudes. What control the numbers of these jets that you can get from the simulations?
Yeah, so they are quite faint, so it's hard to tell, but yeah, they are really small scale. So I would argue, since they are faint and small scale, they should be in gross agreement with the Rhine scale. But well, to be really conclusive on that, you would need to check with different setups that feature different jet size, and so far we failed to really do that efficiently. So yes.
Okay, so let's thank Thomas once more. So now is the coffee break. The official coffee break is a bit shorter than usual. I suggest we reconvene at 20 minutes past 11.
J'ai une question, si t'en as pas marre des questions.
Vas-y.
La première, c'est est-ce que
Pourquoi t'as pas mis une chemise à carreaux? Je
déjà,
n'en avais pas.
Voilà. Désolé. Tu as bien dit que les jets ils étaient liés à des variations de conditions limites thermiques, quoi, quelque part, enfin, anthropiques, quoi.
À la limite de la.
Mais du coup, c'est un mécanisme complètement